So if you're watching this video, you probably already know what the LED Hyperflash problem is. But just in case if you don't, here's a little demonstration. So it's what happens when the car believes one of the indicator bulbs on either the front or rear of one of the sides is out. So it throws a faster blink rate to let you know that one of your bulbs is out. But we can check the car and see that it's not out. So I'm flashing the left indicator right now. The rear one's still on. And the front one is still on. So this is a common problem that happens when people replace their indicator bulbs with LEDs on older cars. And in this video I'll show you a couple ways to get around this problem and talk about the other alternatives to fix this problem as well, and they're not as good. The first one, I guess, is this is the most common one I've seen, is adding a load resistor to the indicator circuit. And it's like a small, I think 6 ohm resistor that you mount on the sheet metal somewhere in the car for heat sinking purposes. And it'll work, but you're increasing the amount of load on the circuit that powers the signals, and it's not really backwards compatible in terms of you can't go back and put incandescent bulbs back in, so you're effectively tripling up on the amount of power that you're drawing on that circuit, and you could probably easily pop a fuse or burn the wires or the connectors or something. So I'm just gonna say, don't even bother going down that route. I'd rather just go back to using the normal incandescent bulbs. The second way that I've seen, that I tried exploring on my own, is through bulbs that have, I have a couple bulbs here, bulbs that have built-in load resistors. They look kind of like this. They're just advertised as no Hyperflash. Let me see what the box says. So I got this on Amazon a while ago, and it says no Hyperflash for rear turn signal, 2 pieces. I mean, it does work. It's rated for, I think, 21 watts, and when you put it in, it doesn't Hyperflash. However, it only works for just 1. So if you install 2, front and rear, then you will induce the Hyperflash condition again, and the car thinks that the bulb is out. And the reason being is that these bulbs still only draw 21 watts of power, and that's not enough for both the front and rear. So if you only draw, I think the incandescent bulbs are rated for a total of 25 something watts, so you're running a total of 50 watts front and rear for one circuit, one, left and right. And if you drop it down to 42, that's enough for the car to think that a bulb is out and throws a condition. So if you just want to run front or just want to run rear LEDs, using one of these is a decent way to go. It'll work, and if you're ever stuck somewhere, you can just go to your auto parts store and replace it with a bulb from the shelf, and you can be on your way again. The other 2 methods I'll talk about are exploring the flashing relay that's in the car that controls the circuit for this, and we're going to talk about how to take it apart, how to figure out what to change and modify to let the car accept the new bulbs without hyperflashing, and keep the hyperflashing mechanism in place in case one of the LEDs do go out. So this video is going to be very long and detailed, so feel free to skip around and find out what you need, or to skip to the end to figure out what the modification is, but I like to go over all the details so you can understand how to come to the same conclusion yourself in case something's different with your car that's not exactly the same with mine. This here is the circuit diagram for how the turn signal and hazard lamps work for that 95 Mercedes. This is a page straight out of Mercedes ETM Electrical Troubleshooting Manual, and it's their illustration for how everything works. So a quick overview. Along the bottom we can see we have all our bulbs. This is the left headlamp unit, left tail lamp unit, and there's the turn signal lamps inside there, and then same thing on the right side. And in the center here we have the instrument cluster, which has its own little indicators inside, along with the audible turn signal solenoid. So this must be what goes click click when you turn the signal on and off. Here we have the combination switch. This is the thing you touch in the car to turn the signals on and off, and it looks like it's just a standard two-way switch. You go left, you go right, and then make some sort of connection with this here line. And then going up the line we can see it runs into the fuse box, and there's some sort of this is the flasher relay I was talking about, so we're gonna go look for this. Some sort of magic happens in here, and I'm guessing the power comes from the main fuse, goes through the hazard switch for some reason, and then angry pixies flow down here and go this way and out to the lamps, the bulbs. And we're gonna have to take this apart and figure out how this works. So we're gonna go in the garage and do just that. So I got my hands on a couple of extra spare units for my buddy Jeff, and the first thing I did was take them apart to figure out what was going on inside it, because we want to see, going back to this diagram, we want to see what's going on in here, see if there's anything here we can figure out why it's hyperflashing. So I went ahead and took them both apart, and we have, looks like we have a couple of coils, relays, a couple of chips, a bunch of capacitors, resistors soldered everywhere, a couple of transistors, diodes, PCB, you know, standard. Same thing here, a couple of relays. It looks almost exactly the same, but the first thing I noticed was this big old fuse here is different. It's not even focusing. There's a big old fuse right there, or something that looks like a fuse, and there's another one right there. They're completely different. And then the other thing I noticed was there's a chip on here. Let's see if you can zoom in a little bit. The chip right here has part number 2043B, and then the other one has a different part number, 243B. So the first thing I did after figuring that part out, went on the internet, went on Google, and I looked up the data sheet for those two chips. And what did I find? Warning or car indication, warning or car direction indicator, or flasher 30 milliohm shunt, pilot lamp to ground, or V battery. So it looks like that chip is very specific to be used in a bulb flasher, you know, for the cars. Now the difference between the two parts I don't really know, except from the description here. It says the 243B is low susceptibility to EMI, and the other one doesn't have any sort of indication about noise. So I'm guessing this one has something to do with, I don't know, some kind of emitted noise, and there's some circuitry to mitigate that. Anyways, I'm assuming these two parts are directly compatible with each other because the application diagram looks, you know, almost functionally the same. So it's probably just a matter of fact, you know, one year Mercedes couldn't buy this part, and another year they couldn't buy this part, or, you know, it's easy to supply one or the other, because obviously these two components, they have the same exact manufacturer part number, so they should be interchangeable, you know. Anyways, the one thing we can see is that this diagram, the electrical diagram that Mercedes gave us, looks really similar to this one. So we have some sort of battery voltage coming in from the top up here, entering in on pin terminal 49, and on the application diagram we have something similar. We have the voltage source, voltage supply coming on terminal 49, running some sort of shunt resistor, 30 milliohm rated, and then there's a relay that is driving some kind of switch, and we go out to the bulbs. Back to the Mercedes diagram, we have the same thing going on. We have terminal 49 coming in from the battery, and we have some sort of resistor right there, and some sort of switch driven by a relay or a coil, and out to the bulbs like we discussed earlier. So let's take a look at the pinout for the chip and how it functions. So it looks like we have 8 pins. We have ground, voltage supply, relay driver, oscillators, voltage supply, again, same as pin 2, pin 7, lamp failure detection, and pin 8, starting voltage, starting input. So we can go ahead and read what's going on here with pin 7. This is the one that's interesting to me. It says something about how the lamp current is monitored by the shunt resistor, and then it does some sort of comparator or comparison with its internal comparator, looking for 81 millivolts. So there's a bunch of math here, and it says blah 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 blah, how to calculate the shunt resistor, and it says nothing about the flashing. Let's see. Here we go. Features. Warning. Warning indication of focus. Warning indication of lamp failure by means of frequency doubling. So what that says to me, going back to the description of pin 7, is if there's a fault detected on pin 7 based on this criteria of seeing a difference of less than 81 millivolts, then the chip will go ahead and throw a fault condition where it will double the frequency of the bulb, the flashing, so which is what we're seeing with the Hyperflash. So how does it do that? Let's go over how this circuit seems to operate, or how this chip seems to work. It looks like we have, under normal conditions, we have power coming through here, and then this looks to be some sort of relay that is closing this switch on and off to drive the frequency, which is determined by this pulse generator, which is probably some sort of 555 timer. I don't know. This is all secret sauce inside. I don't know what's going on in there. But we can also see that it looks like the comparison, the 81 millivolts, is determined here. Somehow we have this V6 here, which is a known value, like a negative 81 millivolts for some reason, and then it does some sort of math on whatever voltage is given after it passes through the shunt resistor, and it does a comparison, and then if it's less than 81 millivolts, then this pulse generator will open and close this relay at a different frequency than it'll open and close it double the frequency than what is normally supposed to be toggled at. So what else do we have here? Pin 8 was that starting voltage. So it looks like at some point we have some kind of starting voltage out on this pin, because we need to be able to start everything. So if you're looking at this diagram, you have to have power here in order for you to click left or right to start the power, to start your signal. Without that starting voltage, there's no way we can know how to toggle this relay on and off. Well, I guess this could be normally closed, and then it can toggle open, but whatever. I don't know the details or how it's designed, why it's designed that way. Anyways, it seems to me we need to modify this shunt resistor to, well, we have a couple options. We can modify this shunt resistor to be a different value, and we're going to calculate the new one given the type of LEDs I choose for my car. Or it seems we can just sever this connection here and either tie it to ground or leave it floating. I'm pretty sure we have to tie it to ground, but I don't know, there could be some sort of logic in here that allows us to leave this pin floating. So what you would do, look for pin 7. So the cheap way, I'll show you the cheap way to do this, cheap, easy way to do this. So here's the index, here's pin 1, 8, 7, oops, can't see it. Here's the index of the chip, of the dip package. Number 1's here, number 7 is here, load detection. What is it? Lamp failure detection. So here is our index. So number 7 is going to be this one here. So if you're really good at soldering, what you could do is this depin number 7 here, or just cut that leg and just kind of lift it up so it's floating, so it's not attached to anything, and that floating might be enough to disable the Hyperflash. But you know, if you disable the Hyperflash, you know, that feature is there for you it's like an idiot feature that tells you that your bulb is out and you need to replace it. So if you disable this feature altogether, you're not going to know whether or not your LED is, your blinkers are working correctly. But if you don't care, you know, it seems like this is the easiest way to do it. Just cut this connection, leave it floating, or if that doesn't work, tie pin 7 to ground. So anyways, we're gonna go ahead and do some math and figure out, based off of what they supply us here. We're gonna do it in 2 ways. We're gonna follow Ohm's law here and figure out from here what the correct resistance should be. And then the other way we're going to look at it is the voltage divider. So when I was looking at this diagram, this looks like a voltage divider circuit to me, and I'll go over that in a second. But first we're going to just run through the math and figure out what this value should be. So before we move on, I wanted to hook up the relay to a bunch of wires and powers and just see what was, you know, see how it operated. So I have a power supply on my left here. I can supply 12 volts. I have power and ground connected on 49 and what is that, 30 for ground. And then I connected these two 1157 LEDs, not LEDs, filament bulbs, and I'm connecting the power from the switched 49 directly to the higher power filament on the dual filament bulbs. So when we turn on the power, we get the flashing. So it's working. So if I disconnect one bulb, this should put it into hyperflashing mode. And if you look carefully, if you look closely and see if I can zoom in on here, we can see exactly which relay is clicking. The one in the center right there. And then there's another static test. So I was really curious about, zoom out. I was really curious about this starting voltage being on 8. So I metered it out all the way from, where was it? From 49 to 49A, and there's no continuity when the relay is not powered. So the only way it can get voltage is through the starting input. So it seems like to me something happens in this box. We supply a starting voltage here, and once the system starts going, it starts generating a pulse, then we turn off power from 8 and we supply it straight from here, or something like that. I don't know. It doesn't matter. The next thing I wanted to do was measure the resistance, or we can actually just measure the power draw of just one of these bulbs. I'll get a clips. Let's just measure the power draw and we can figure out what the resistance is. Let's bring this into view. Okay. Focus. Okay. So with 14 volts we're pulling 2.3 amps. So I think that's something like 6 ohms. I don't know. I can't do the math right now. We'll figure it out later. That's how much one of these filament bulbs pull. We need to do the same thing for the new LEDs we're going to be using. So I made the same dumb mistake again and bought some new made in China cheapy LEDs off Amazon. But instead of being the 21 watt high powered built-in load resistor garbage, this is just a standard 5, I believe it's like 5 watts, low power LEDs. And the cool thing about this LED is you see here it's got both amber and white LEDs on it. So it's like a switchback LED. So the 1157 is a dual filament bulb, and this LED counterpart or copy, it does white and amber. So when you're indicating on the high power line, one of these two, I don't know which one it is, the casing is ground, and one of these two contact points is for the high power signal, and then the low power running light. So when you're on the running light, it'll use the white LEDs, and then when you're on the high power side, it'll use the indicator orange LEDs. So we'll go and measure how much power this one uses really quick. Let's see if I can figure out how to plug this thing in properly. Alright. So it looks like it's pulling 240 milliamps. It's like a tenth of how much the filament version was using. And then if we connect it to the other line, you'll see that the LED glows white instead of amber. Also around 230, 220 milliamps, whatever, somewhere around there. And of course, we cannot forget this little baby indicator light, the one that goes inside of the instrument cluster. These things are really low power. They're about 1.2, 1.3 watts rated. But since the LEDs we're dealing with are in that same range, it'll make a significant difference in the numbers that we come up with. So let's go ahead and measure this really quick. We'll hook it up. So 14 volts, it looks like we're pulling about 90 milliamps. So we'll go ahead and take all the numbers, take all the data, and put it through the calculators on the computer and figure out what resistor we need to use. Okay, so we did all that testing, we grabbed all the numbers. Now we're back on the PC, we're looking at the data sheet, and we're looking at all the numbers. So what we know is that the original stock filament bulb at 14 volts pulls about 2.29 amps. The LEDs, they pull about 240 milliamps, 230 milliamps. And then the little tiny cluster bulb inside your instrument cluster that blinks, that tells you that which side you're blinking, that pulls about 0.09 or 90 milliamps at 14 volts. So going back to the data sheet and looking at how that shunt resistor value is calculated to be 30 milliohms, we'll just follow along. The way they do it is they say for one bulb at 21 watts is about 1.75 amps. So doubling that for 2 is about 3.5. And they say the detection threshold is recommended to be set in the middle of the current range at 2.7 amps. So setting it in the middle of the range kind of gives you a little bit of buffer space or a little bit of room um, for different manufacturing tolerances. Maybe one bulb is 22 watts or 23 watts, or another one's like 19. So 2.7 is kind of a good conservative way to set a threshold. Put it right in the middle of the range. So given that their target value is 2.7 amps for triggering a bulb out condition, what they do is they just use that in Ohm's law with the threshold of 81 millivolts across 81 millivolt voltage drop across the shunt resistor. You put that into Ohm's law and you wind up with 30 milliohms. So we're going to follow the same method except with a little tweak. That little cluster bulb needs to be factored into our calculations because we're dealing with something in such it's very close to the LED's power draw, so it creates a significant enough of an error to show up in the results. Whereas if we're looking at the standard filament bulbs, they're pulling what, 2 amps, 4 amps of power. 90 milliamps is not going to create any sort of significant error to throw off the numbers. But since we are down in the milliamps range, this 90 milliamps is going to cause some problems. So we're going to insert this into our numbers as kind of a baseline. So this will show up, we'll add it into a 1 bulb nominal current and a 2 bulb nominal current, and then we'll just take the average of the two. So how that looks is something like, let's see, 0.09 plus 0.24. So this is for 1 bulb. So we have 330 milliamps. And then if we wanted to do 2 bulbs, 0.09 plus 0.24 plus 0.24. Let's just round it up to 0.24. So these are our current ranges, 0.33 and 0.57. So if we just take the average of the two, we get 450 milliamps as the recommended detection threshold. So taking that and putting it into Ohm's law, we should be able to figure out what the resistance should be. So what did I say, 0.45 and 14 volts. So this should give us, oh no, that's not right, 0.45 and 81 millivolts. That gives us 180 milliohms. So that means our shunt resistor, or R3 in that circuit, needs to be replaced with a 180 milliohm resistor in order to avoid hyperflashing with LEDs installed, but also keep the hyperflashing feature enabled in case one of the bulbs front or rear do go out. So there's another way to kind of double check our work here and kind of see what's going on from a different point of view. The circuit that is drawn for the datasheet looks very, very similar to how a voltage divider circuit looks. So we have the source voltage on the top, we have the source supply voltage on top here, and then that runs across a shunt resistor R3, which is the equivalent of R1 in the example diagram, and then R2 is the equivalent of all of the bulbs combined together for either the left side or the right side. So the way this looks as a voltage divider example is they want pin 7, the potential difference or the voltage between 7 and ground versus voltage supplying ground to be a difference of 81 millivolts. So what that means is if we're having 14 volts, the difference of 81 millivolts will bring it down to 13.919. So we want to see this V out to be 13.919. So if we had, let's assume we did everything right, our source voltage is 14 volts, our R1 is going to be 180 milliohms from our previous calculation, and resistance 2 is going to be it's 3 parallel resistors together. What I have for the values here, 3 parallel resistors, so R1 is going to be this, 58, 61, and 156 ohms. That's the equivalent of 24.97 ohms. So 24.97 ohms. If we calculate, if we were running a 180 ohm resistor, the voltage difference or the voltage output here is going to be 13.900, which is less than what we calculated the threshold to be. So the threshold would be 13.919 to trigger a bulb out condition at 14 volts. So the voltage drop across a 180 milliohm resistor will be enough to satisfy that. So you can put this into, you can put the numbers in this calculator, kind of dick around with what you would get. So given that 24.97 is correct and accurate, we can kind of just fudge the numbers here. So what would happen if we had a 200 ohm resistor or 200 milliohm resistor? It would bring the voltage drop a little bit more to 13.889, which it's kind of, we're going more conservative to avoid the false bulb out condition. So it looks like the higher we go, say it's 250, bring to 861, which is less than 13.919. So looks like the higher value you go here, the more voltage drop you'll see across R1, but then you run into a problem where if you drop out one of the bulbs, then you will no longer hit the threshold to create hyperflash when the bulb's actually out. But I'll leave that for your experimentation. So what we're going to do now is go look for a 180 milliohm resistor on Mauser. You can use any that you want, but passive components, resistors. I just want to point out something about the resistors when you're going to go pick one. I'm going to go for an axial, and let's look for somewhere around 180 milliohms. Perfect. These two. Okay, so I wanted to point something out. When you're looking for the resistor, you want to find the highest power rating available that will fit inside of, or fit your application. The thing I want to note that is the higher the power rating you choose, the larger the physical body of the resistor is going to be. So for example, this 20 watt rated resistor is going to have a 63.5 millimeter length. So the body of the resistor, the square part, is 63 millimeters large. So that does not fit inside of the relay box that I have, so I have to find something smaller. So 20 watts is out. And the reason why you want a higher rating for the resistor is that all of the power for the indicators, all the current is flowing through this line here. It's flowing through R3. You choose one of the cheapy resistors you find at a hobby store or like at I don't know, Radio Shack's not there, like Fry's Electronics or something like that. Something like a quarter watt rated resistor. That thing will likely melt down and cause a fire if something were to happen. Like say you sold the car and the next owner, the bulb went out and they went to the local AutoZone and bought like a just some sort of 1157 replacement LED or 1157 bulb and just put it in the car and turn on and start using it. All the indicators would immediately just die because the resistor would just burn up and not be effective anymore, completely useless and broken, or it would cause a little mini fire and cause something else to go wrong. So you kind of want to find a resistor that's higher rated than, quarter watt. And general rule of thumb, I believe for these kind of resistors is the power rating that they advertise. It can be overloaded by 10 times the rating. So for example, this one, the 7 watt. I'm just pulling up a random data sheet here. I haven't even reviewed this yet. Let's see. Usually there's like a rating for how they determine the power. There's something about like here we go. Short-term overload. This one's a bad example. Let's find another one. Here we go. Short-term overload. 10 times rated power, 4 watts and larger for 5 seconds. So that means, usually the power rating is for continuous use, so current is constantly flowing through the resistor. But since this is since we're using these for indicators, they're not on all the time. They're on for like fractions of a second and then off again. So if we need to be able to be backwards compatible up to, 21 watts for one bulb, times 2, that's, let's just say, max it out at 50 watts. We want to find at least a 5 watt resistor when we're looking for the 180 milliohm resistor. So, like I said, the bigger the power rating, the bigger the package, the smaller power rating, smaller package. So try to find a happy medium and pick one that you like. So I will probably look for something around a 7 or 5 watt resistor that will fit inside the relay box that I have. And I'll go ahead and order something and then we'll solder it in. Now before we do that, I'm thinking why don't we just go ahead and test out what happens when we try to disable Hyperflash altogether. I mean, the easy solution. The easy solution being no math required, no thinking, let's just cut out pin 7 and see what happens with the chip. See, it should allow us to disable Hyperflash altogether. And for one of the relays, pin 7 would be this one here, but it's really tight and close to this capacitor. Let's check out the other one. This other one looks like it's a little bit easier. There's some more space. It's the same pin. A little more space between here and here. So maybe what I'll try to do first is, I don't know, I might try to desolder, I think this is pin 7 right here, desolder this one and then try to push the leg out so it's not touching the through hole anymore, and that should effectively let us, it's the same thing as removing this pin altogether from the circuit. But then if I can't do that, let's go ahead and bend this forward and give that little leg a cut with some snips. See what we can do. Since that was impossibly difficult to do by myself, I went ahead and just cut the leg out. And let's get her hooked up and see if it'll still hyperflash. Alright, moment of truth. So it looks like with a single bulb and pin 7 cut and left floating, the single bulb will not cause a hyperflash anymore. So it looks like that's the cheap and easy way to do this fix. Okay, it's been a few days. The resistors are here from Mauser. Here's the 180 milliohm resistor. Order about 5 of them. This is what the 5 watt, 5% resistors. It's like what? It's like 18 millimeters in length or something like that. It should fit. Let's pull one out. It should roughly fit inside of the relay package, I hope. Yeah, that's not going to be a problem. So I just need to trim the legs and solder into where the old shunt resistor is at, and that's it. I also want to go ahead and show you, I also ordered a bunch of other resistors as well. I wanted to show the size difference between going up in power rating. I think this one was a 15 watt resistor, so this one's a lot larger. You see it's significantly bigger. So the bigger the power rating on the resistor, the larger the package. So I mean the heat's got to go somewhere, so it goes in the body of the resistor. So that's a 15 watt, and then I have a 7 watt 220 ohm resistor. So this is just a little bit bigger. Looks like a little thicker. This one's thinner and longer. The other one's thicker and shorter. They come in different flavors and sizes. And then, do I have any other ones? 5 watt. Here's another 5 watt. It's about the same. It's a little smaller. But you get the point. I'll go ahead and do the next part, which is desoldering the shunt resistor from, well, not this one, the other one, and then putting it in place. I will say that sometimes these helping hands are more like hindering hands. Not very fucking helpful sometimes. Come on. Fucking. Is that what I want? Good enough? Okay, that's one part of the arch removed, and let's see if we can get the other one out. Just like that. Ooh. Here we are, McDonald's arch in its glory. So what we're going to do is just go ahead and solder the new resistor in place through the same holes. That should do it. So the height is good. We're not shorting anything out. Looks good. See, and we will have these little things here, but we'll just cut them out. Okay, looks like it's ready. Just put it back together in its casing and go test it out. And I put a little label on here just to let me know that I have a 180 milliohm shunt resistor and it's meant for a 5 watt front, 5 watt rear, just in case I need to figure out what the hell this is. And we'll just put the relay right back in the car. It goes right here. Alright, we can do a little test now. Okay, so here's the test. What I'm going to do is turn on the indicator, and that should blink at the normal rate with the LED. And then I will run to the trunk and pull the rear corner signal bulb out. And then when that bulb comes out, the bulb in the front should throw the fault indicator and start hyperflashing. Okay, there you have it. The relay modification worked. So now what we have is low-powered 5-watt LEDs in our indicator bulbs, and it does not throw the hyperflashing condition anymore under a false, low current condition, because we've successfully modified that shunt resistor to be detecting a smaller, 5-watt load on front and rear. And then on top of that, we also were able to pick the correct resistance such that if one bulb is faulty or out, it will still throw a bulb out condition and begin the hyperflash to let you know. So that concludes this video. If you have any questions on the subject, or there any sort of detail that I glossed over probably, go ahead and leave comments in the questions in the comments, or just send me a message directly. Thanks.